Okay, next in this class we will discuss few aspects of these macrocycles. Number one is macrocycle, as you can I will write macrocycles. Here is a macrocycle. Only one type of donor, that is X. So, when X is nitrogen, phosphorus, sulfur, etc., they prefer to bind, they prefer to complex transition metal ions. Okay. And when they are oxygens, when they are all oxygens, like a crown ether, then they will prefer to complex alkali or alkaline earth metal ion. Now, which metal they will bind? Suppose this one, which metal this will bind? If there are all four X is are oxygen, it will bind an alkali metal. Let me draw this ether. Okay. If these are all oxygen, all oxygen, then the size matching, the whole size, this whole size must match the size of the alkali metal I am talking about. See, this macrocycle is pretty big, and when lithium binds, for example, when lithium binds, lithium ion binds, lithium plus, when it binds, what is meant by size matching? Lithium oxygen has some bond length, say 2 angstrom. Okay. So, if a lithium can be coplanar, that means in the same plane as these four oxygens, all right, and at that point, at that conformation of the crown ether, the lithium ion can be coplanar with these four oxygens and binds inside, so that all bond lengths are equal and very close to 2. Okay. So, then we will say size matching perfectly. But suppose here is a, instead of lithium we have a sodium. Sodium is much bigger, its ionic radius is much bigger. So, is oxygen, his bond length from sodium ion to oxygen will be little bit more. So, that means it will not fit here. Then what will happen in that case? Sodium ion will be above the macrocycle, somewhat above the macrocycle. Okay. So, it will not be that stable compared to lithium, because lithium can be inside the macrocycle, coplanar with these four oxygen and nicely binds. So, when we say size matching or size mismatching, this is what we understand. And here I have put lithium because these are all oxygen donors, and if we have a say all sulfur donors, you know that sulfur likes heavy metals to bind heavy metals. So, there could be a sulfur, okay. There could be sulfur like this. So, a heavy metal will try to bind, depending, but it cannot enter here. Okay. So, what we need? We need maybe bigger, somewhat bigger. Then it looks like it is also, so the people are always trying to have systems where the macrocycle, where a particular macrocycle specifically bind a metal ion. So, some ground rule exists, but we have not been successful in having macrocyclic compounds which will specifically bind a particular metal and not any of the others. That is still not realized, but we have understood few things. So, that it goes on with that. For example, this when we have this oxygen which is a hard donor, okay, hard soft acid base principle. So, according to the oxygen is a hard donor and sulfur is a soft donor. So, when we have a mixture of that, then interesting binding can be expected. Okay. I am just writing this. Okay. Interesting binding of ions can be expected with this. So, all these things have to be understood, have to be synthesized and have to be understood very slowly. There are two aspects: the macrocycle, size of the macrocycle and nature of the donors. So, all donors may not be same, or all donors are identical. Okay. All donors may be different, oxygen, sulfur, nitrogen, like that, or phosphorus, like that. Mixture of donors, they are possible, or some pure, only phosphorus, only sulfur, only oxygen, like that. So, depending upon that, their binding ability towards different types of metal ion. All right. Now, I will tell you another is called the macrocyclic effect. The macrocyclic effect is that an important aspect of this cyclic compound is that compared to linear compound with same donors. For example, suppose this compound I am just writing this, does not mean just an example. This particular compound with secondary amino groups, this particular compound binds say a nickel 2 plus very strongly. It binds very strongly to nickel 2 plus because size matching, again size matching you understood. Now, all right, compared to if I get a compound like this, NH2, okay. Okay. This is an open chain. So, open chain compound also makes pretty good nickel 2 plus. Nickel 2 plus, but what happens compared to the open chain, this macrocyclic compound complex, when it complex with nickel 2 plus, it has extra stability compared to the identical, compared to this what is identical is not identical. I will to draw this, then it will become identical. Hang on, it's called messed, it is all mess up. Let me draw. I will draw. Yes. So, these two are, this is a acyclic analog of this cyclic compound. So, the extra stability is called macrocyclic effect. So, I will say that macrocyclic compounds, they bind metal ions with increased strength increase strength and stability compared to their open chain analogues, and this extra stability is termed macrocyclic effect. So, their extra stability is that thermodynamically much stronger. Okay. This compound is extra stable compared to this compound, although they are structurally are same, okay, similar. This is acyclic analog. So, macrocyclic effect is the extra stability. Why? See, in this delta G, it has both thermodynamic stability and kinetic stability. Let me explain. In this equation, what happens? It has entropy and it has enthalpy contributions. What happens? What happens to entropy? Entropy does not change very much upon metal complexation. Okay. Why? Because this compound is already arranged, till it is existence is already arranged. Okay. So, all these nitrogens are bound here and you have a macrocycle. So, once the metal ion goes in, there is not that much of arrangement necessary. Okay. So, delta S contributes slightly positive, but not much, but delta H is very high. Delta S is not much, but delta H is very much negative. That means, these bonds are very strong, much stronger than here. So, therefore, that extra stability here comes mainly through delta H thermodynamically. That is one thing. How about kinetic? Just look at this compound. From this compound I can easily get nickel out if I put any salt or what, because this amine group at the end they can actually come little bit with little bit of energy. If you give, it can come like this, say 1, 2, it is coming falling apart. Similarly, this one falling apart, let us see. Slowly it falls apart and in a suitable condition nickel can be easily recovered. How do you recover nickel 2 plus here? You have to cut. If you cut it, suppose I cut this somehow, but then this amine cannot run away because this macrocycle is already there. So, immediately it will bind, it will bind like this. So, how I can get the nickel out? I have to cut all 4 together, all 4, all these 4. I have to cut this, cut this, cut this and cut this, then only nickel 2 will come out of there. So, that is kinetic. Okay. So, both thermodynamically and kinetically is favored over open chain compound, and that is called macrocyclic effect. Another thing you have to understand that macrocycle, okay, maybe I will try this. Macrocycle, when they are in free state, okay, they are not, when I write this, say I am writing this 1, 2, 3, 4, say this is a macrocycle. Okay. And this macrocycle molecular mechanics, when there is it is a synthesized, is a pure organic compound it has no metal, nothing. So, this particular compound, if you do molecular mechanics calculation, you will find that 3 oxygens, alternate oxygens are up and 3 are down. So, 3 oxygen atoms like this one and this one, they are up and 3 are down, that is the conformation, and that is called D3 conformation, D3D. In symmetrically there will be D3D, or they are or they are or they can form an elongated compound without any symmetric up and down, then it will be Ci. Okay. So, when they are D3D, they can bind pretty well a metal ion. When they are Ci, that must be transformed into D3D under the influence of the metal ion. Presence of metal ion will influence it to change from Ci. Ci I am not able to draw. Okay. Ci, these are point group symmetry. Okay. Here I am saying that 3 up, 3 down nicely. So, it is D3D. Here I am unable to do that because it is computer drawn, and I will not try to do that, but it is an elongated. So, if that elongated thing has to bind a metal ion, what will happen? What it will do? It will change from Ci to D3D, and for that changeover it needs energy. So, therefore, delta G will not be that much negative. So, these are all thermodynamic aspects of metal binding and size selectivity of these particular macrocyclic compounds. Then I will try. So, these are aspects of macrocyclic and metal coordination chemistry, which I will describe again and again throughout as we proceed in these lectures, because they are very useful. These macrocycles, metal macrocycles are very useful. Okay. But a macrocycle, when it binds, like I said in case of nickel, in here when it binds, it is quite stable and all that. However, even then there is a chance that it can be attacked from top and bottom, because top and bottoms are still available for attack. So, what will happen? To change that, because it is bound in a linear in a coplanar, so top and bottom can be attacked, can approach another ligand can approach from top, or it can approach from bottom. To avoid that, what has been done? We can do something called Lariat ethers. This is I am drawing a picture of a Lariat ether. Hang on. Say, all right, I will draw a picture of Lariat ethers. Here I will put a nitrogen and 1, 2. Okay. So, here is a say ether compound, aja ether, and then if a metal ion is inside, it can be attacked. So, a potassium ion can be inside, it can be attacked from top or from bottom by another ligand. Okay. So, therefore, what I will do? I will put I can functionalize this secondary amine. It has been functionalized with this kind of extended arms attached, OME, okay, or OME, or say this kind of compound also exists, oxygen, oxygen. So, 2 aja. 2 aja, 18 crown 6. Okay, so here is nitrogen. So all I can do, what one can protect from top and one can protect from bottom also. So that the when some metal is here, an alkali metal, alkali or alkaline earth, then this alcoholic group, this can come, OH group, it can come here and hydrogen will go and O minus from top and this one can go bottom. That means, here is a macrocycle and here is a arm here, it can come from here and this arm can come from bottom. So, the top and bottom and these sides all are coordinated, all are safe. So, the metal will become very stable, metal inside this cage. Of course, all this goes with it, size must match, which metal will go and etc. So, this kind of compounds are called Lariat ethers, Lariat ethers. There is a large number of Lariat ethers known in the literatures, all right. So, these are Lariat ethers, I have drawn couple of here and then, so these Lariat ethers can be used to protect and some other supramolecular catalysis, there are many things are there. As we go along we understand. All right. So, this concludes the crown ether part. So, and so first synthon that I did, supramolecular synthon, is crown ethers and macrocycles. Okay. So, macrocycles means any other not ether, non-ethers macrocycles like aja, thia, okay, that compound or simple crown ethers and also Lariat ethers. So, now I will start something called another one, something called calixarene. My second synthon will be calixarene. Calixarenes. Okay, calixarenes are very interesting compounds because calixarenes are macrocyclic phenols. Okay, this is a gentleman called von Baer. Okay. This person found that if you react phenol, a phenol with aldehyde like formaldehyde. So, he found that phenols can react readily phenols with aldehyde or specifically formaldehyde, then it can form a resinous material or a plastic phenol formaldehyde at high temperature. So, it can form phenol formaldehyde resin and that is very popularly called bakelite. okay, bakelite plastic, that was discovered long time ago, when 1870s, 1870s, so more than a century. Okay. So, phenol formaldehyde resins or plastic, they are called resins and plastics, they are called depending upon the synthesis and how you cook them, what temperature, how long, etc. So, they found that it can be very interesting plastic materials and they call it bakelites. Okay. It was synthesized in 1870s, but so phenol when reacts with formaldehyde can give a mixture of oligomers, okay, that is called resinous materials, and sometimes it can also form plastics or bakelites. Okay. So, now what happens is, if we do para substituted phenols, then it was discovered that para substituted phenols, those were unsubstituted phenols, and this is para substituted phenols reacts with aqueous formaldehyde, Okay. So, there could be then it can react with linseed oil. Why linseed oil? Because we can achieve high temperature 200 degree, several hours. So, reflux para substituted phenol with aqueous formaldehyde for several hours, sometimes days also, then you get a mixture of under basic condition forms a mixture of macrocycles. And these are called calixarenes. Okay. So, therefore, calixarenes we can get calixarenes or these macrocycles we can get if we in a controlled fashion we react para substituted phenol with aqueous formaldehyde, we get this mixture of macrocycles called calixarenes. However, if this is unsubstituted, then you can get this plastic. So, our desired compound we can get only with para substituted phenol and aqueous formaldehyde in linseed oil at 200 degrees centigrade for several hours, we reflux it, and finally, we get these macrocycles or calixarenes. Calixarenes, or these are also looking like a basket molecule, very fine, is a very interesting compound, series of compounds, okay, calixarenes. Thank you.